Standard ROS messages like std.std cover basic telemetry. But when a robotic arm executes a rapid sequence of precise movements, it requires highly specific, bespoke data commands to coordinate joint states and targets. This network topology diagram shows our objective. We are going to build a custom ROS package to route specialized data. We will create a custom robot status message, a set goal service, and the Python scripts to operationalize them. To follow along, you need a functional ROS1 installation and an active Catkin workspace initialized on your system. Moving beyond default message types allows you to tailor your data pipelines directly to your hardware. You design the exact communication structure your robot needs to operate efficiently. This terminal mockup shows the exact command needed to create our new package. By typing catkin create package myrobotmessages std messages ropey, we establish a new directory that pulls in standard message types and Python support. Inside that new package, we need two dedicated subdirectories, one named MSG for our messages and one named SRV for our services. Looking at this code editor, we see the raw text for our robotstatus.msg file. We define the structure by listing the data types, string and float32, followed directly by our specific variable names, status and battery level. For our service file, setGoal.serve, we must divide a request from a response. We put our float inputs at the top, the Boolean output at the bottom, and separate them strictly with 3 dashes. Defining these data structures independently from your scripts ensures that your system stays modular. If a sensor requirement changes later, you update a single text file without breaking the rest of your network. Next, we update our workspace manifests. The package.xml file tells the ROS compiler what dependencies it requires to build and execute your newly drafted files. This package.xml mockup shows the 2 required additions. We add the XML tags for message generation as a build dependency and message runtime as an execution dependency. We then modify cmakeLists.txt. Missing a required dependency in this specific file is the most common cause of build failures, so we have to update several blocks. In the find package block of this file, we make sure message generation is explicitly listed under the required components. Then we explicitly register our 2 files. We place robotstatus.msg inside the add message files block and setGoal.srv inside the add service files block. Finally, we uncomment the generate messages block to establish the link back to standard ROS messages like std messages. Configuring these 2 manifests is required so the compiler knows exactly how to translate your raw text definitions into the executable Python classes your system needs. This terminal window shows the build execution. We navigate to the root of our workspace and run catkin make. The logs confirm our package compiled successfully. After a successful build, you must run the setup bash script to register these new packages with your environment. Skipping this sourcing step leaves the operating system blind to your compiled files, which causes an immediate module not found crash the moment you try to run your Python scripts. With the environment prepared, we write the programmatic logic. First, we create a Python publisher script designed to loop continuously, broadcasting our custom robot status data at 10 Hz. Looking at the publisher script, we use this exact import syntax to connect our generated package to the Python logic, pulling robot status directly from myrobotmessages.mess. Next, we write a client script. This logic waits for the custom service to become available and then transmits our target X and Y coordinates to the robot. In the client script, the import syntax required brings in both the custom service and its associated request object, using from myrobotmessages.serve import setGoal request. Before executing, we modify the file permissions of both scripts using chmod plus X to make them fully executable. These 2 scripts act as the operational layer. They take the abstract network configuration we compiled and use it to drive tangible behavior. This split-screen terminal shows our operational sequence. We start ROS core in the background, launch the active publisher script on the bottom left, and execute the client script on the right. Looking at the client output, the service takes our coordinate inputs and returns the Boolean response, goal set successfully. Bidirectional communication is confirmed. As you move to ROS 2, the build system shifts from catkin to ROSITL. However, the structural logic of defining data outside of your scripts remains exactly the same. Building your own data structures frees you from generic templates. You dictate the exact flow of information, giving you total authority over the architecture of your custom robotic system.